Hello everyone and welcome to today's webinar. Sorry for the delay, we had some technical difficulties. My name is Robert Salka and I'm part of the technical team in the London office of MIDAS. And today for the next hour or so we'll see how dynamic analysis for high-speed rail can be done in MIDAS Civil. So let's see firstly the topics of today's session. So we'll look into when is dynamic analysis relevant or required. We'll see how to set up an eigenvalue analysis, how to add mass, how to set up time history load cases, and how to generate and how to apply the train loads to the structures, and then we will see some checks of some results. And at the end, for about half an hour or so, I will show a demo on how to do this from scratch to reading the results. So let's start. When is dynamic analysis required? Basically, you can carry a dynamic analysis whenever you find relevant, and authorities in charge of the project can choose if they want to have dynamic analysis run or not. But if that is not clear, the Eurocode provides some steps for us to see whether a dynamic analysis is required for our structure. And there are several items that define whether this is relevant to us or not. And these are the complexity of the structure, then the maximum line speed, and also we're interested in vibration properties of the structure, so the natural torsional frequency and the natural bending frequency, and also the maximum nominal speed. Now, before running a dynamic analysis, it is always mandatory to run an eigenvalue analysis. For this, MIDAS Civil offers different analysis types to be chosen for an eigenvalue analysis. So we have subspace iteration. This is probably the most commonly used type of analysis for eigenvalue analysis, and this is very effective for large structures, so the computational time for large structures is very small. And also Landsource is available, and this is very efficient when it comes to lower modes. And another type of analysis available is that of using risk vectors, which calculates the vibration properties considering loading from a load case that we define. And this is reliable when it comes to structures that have fewer modes of vibration. And just as I said, every dynamic analysis needs to be preceded by an eigenvalue analysis. This is for being able to be able to run the dynamic analysis, and also there are checks that need to be done for the vibration modes of the structure. And in order to run an eigenvalue analysis, we always need masses. In MIDAS Civil, we can consider masses in the structure in two ways, either by using lump masses or consistent masses. Lump masses basically considers that the distribution of the masses is only concentrated at the nodes. So we will have a diagonal matrix of the masses with the mass lumped at node level. The other way of considering mass is by using a so-called consistent mass. The mass matrix in this case has a form similar to that of a stiffness matrix. The mass is considered to run along the elements that are found between nodes. Now there are also, let's say, two different ways of applying the masses to the structure. The easiest way is by simply converting load cases that are already in the structure into masses. We can convert the self-weight function directly using the option here in the structure type window, and this also allows us to choose along which direction we want to consider the mass. For example, for tall structures where the horizontal displacements are the most relevant ones, we can convert only to x and y, so to the horizontal plane, in order to save computational time on large structures. And alongside self-weight, we can also include mass from existing load cases. So if we have non-structural elements, the loads from non-structural elements in the model, we can simply convert those to masses as well, considering nodal loads, beam loads, floor loads, or pressure loads. We can simply choose a load case and assign a scale factor, and then the value for the gravity and the mass will be automatically calculated. If there are masses that are not present in the form of loads in the model, we can also directly apply masses at node levels by simply using a function called nodal mass. Now, after setting up the eigenvalue analysis and adding the masses, we can continue with defining the time history load cases. Within one model in MIDAS, we can run several time history load cases, considering different train speeds or different types of time history analysis. Now, we support both linear and nonlinear analysis. For linear analysis, we can use as an analysis method model analysis and direct integration. And as a time history type, we can choose either transient or periodic. Whereas for the nonlinear time history analysis, we can use model, direct integration, and static, but only a transient time history type. Now, it is very important to know from the beginning what type of excitation we add to the structure, so what type of loading we consider, and that will tell us what type of history type to use. For example, if we have train loads, earthquakes, or if we are analyzing a pedestrian bridge for walking and jogging loads, then we need to use a transient time history. Whereas if we are analyzing a structure where we have machinery, so where we have cyclic loading, or if we're analyzing a pedestrian bridge for crowd loads, then we need to use a periodic time history type. Now, maybe the most complicated item to consider when it comes to this type of analysis is damping. Now, there are four types of damping available. Maybe the most commonly used is modal damping. The Eurocode also helps us with choosing the relevant damping ratio, critical damping ratio for our structure. Now, we can also assign damping proportional to mass and stiffness. We have options to choose which of these should be relevant in the calculation of the damping. And when we have more complex structures, or structures where we need to use, when we have different structural materials, each of them with different damping properties, or when we include dampers or base isolators in the structure, we can use strain energy proportional damping, and also what's called Rayleigh damping, or element mass and stiffness proportional. Now, as I mentioned, the Eurocode helps us in choosing what damping ratio to use in our analysis. This is relevant to the span length and also to the type of bridge. And also, when it comes to span length of smaller than 20 meters, then we need to add an additional value to the damping in order to avoid the reduction of peak response at resonance. Now that we've set up the time history load cases, we can continue with adding the loads. Now, in MIDAS Civil, we have a so-called train load generator function. With this tool, we can generate the loading from any type of train available. We also have a database of trains available, but we can apply any type of train. So if, say, for a new project we have a special type of vehicle, a special type of train to be considered, we can easily incorporate that in the model. So, for example, here I've just taken a high-speed load model A, and we can simply add all of the values, the axle number, length to the next axle end loading, and force per axle, and we can add it directly in here. or we can even have this created in an Excel spreadsheet and then just import the spreadsheet, just as I will show you later on. We choose train velocity and also, very important, the distance between the nodes, because as you may know, dynamic loading in MIDAS Civil is applied at node level. It can be applied in many different ways, but for high-speed trains, the easiest maybe is using dynamic nodal loads. So then the deck should be divided in so that this element size is also found along the deck. So once we've input all the information about the train, the function will generate, the tool will generate this function for us, where we have the loading and a long time, and we can export this and import it later on in time history function. Simply import it, and then we can continue with applying the actual loads. Now once we have the time history function, we can select a node and select the time history load case that we want to apply this load to, and also the function, direction, arrival time, and scale factor. Now we can do this for every node along the deck, but maybe the easiest way is to use the code-based input in MIDAS Civil. This is done using the so-called MCT command shell. Now once we've applied the dynamic load to one node, we can get the code-based input for that is internally used in MIDAS Civil, and we can see the pattern and how the values should be arranged so that we generate the load itself. And then in a simple Excel spreadsheet, we can easily create this format and then simply run it, and it will be applied just as you see in the screenshot below along all nodes of the deck or of the rail, depending on what we choose to consider. Now once we've run the analysis, once we set up everything and run the analysis, we need to check the results. Now maybe the first and very important aspect to check is vibration properties of the structure. Now we can check vibration modes and the frequencies of the structure directly in a visual form. We can check each mode that we've considered directly here, or to have a sum of the entire structure and all the vibration modes, we can check these in a table format. It is very important to always remember and take into account the frequencies of the structure. You will see later on how we will check these against excitation. And another important factor to consider, as you may know, in order to make sure that we're considering all the relevant modes for the structure, all the relevant vibration modes of the structure, we need to make sure that more than 90% of the mass in the structure is excited by the load. So we can check the modal participation masses for each direction. And if a general rule is 90%, so if 90% is not passed, we can go back, increase the number of frequencies that we want to assess, and then go back, reanalyze, and check whether the 90% threshold is passed. After checking the vibration properties of the structure, we can continue with checking the actual results from the dynamic analysis. Now, what is in the deck acceleration is important for preventing track instability, and also it is important for the comfort of the passengers. Now, the acceleration of the deck can be checked for each node along the deck visually in, let's call it, a deformed shape of accelerations. But maybe the easiest way is to just create a time history of the acceleration for a node or for the nodes that we're interested in directly in a graph. So we can check, for example, here I have two nodes and I'm checking the acceleration for two nodes a long time in this time history load case. And then once we've made sure that the acceleration value is not passed, so the requirement is fulfilled, we are also interested in making sure that the excitation applied to the structure coming from the train load does not match the resonance of the structure. Does not match the vibration properties of the structure. So we don't want to have the same frequency as the frequency of the structure. Now, once we have the time history here, we can easily use an FFT transformation to get a plot of the energy added to each of the frequencies of the excitation. So for example, we can see here that most energy goes into this frequency, and then we have this peak here and this peak, and then we can go back and check them with the actual frequencies of the structure. Now, a so-called test, but this is something that train enthusiasts generally do, is a so-called coin balance test. Now this, what they do is just hop on a train and put a coin on the sill of the window or on the table and see if at full speed if the coin is balanced. And you can imagine that if 320 kilometers per hour the coin doesn't fall, then the ride is smooth enough. Now, on top of this, we also need to check forces, deformations in the structure. Now, the Eurocode says that we need to check results from the dynamic analysis against the results of a static analysis enhanced by dynamic factors. Dynamic factors can be directly included into high-speed load models here, or if we're running an analysis, a moving load analysis for load model 71, SW0 or SW2, we can have the dynamic factors automatically calculated by simply defining the determinant length and the quality of the maintenance for the track. And also, if we have different structural elements, and so not only one main deck element, we can apply dynamic factors to every type of element. Now, just like moving load analysis, time history analysis gives us envelope results. These envelope results can be directly placed into load combinations. So we can create load combinations considering dead loads and the train loads coming from the dynamic analysis into a load combination and compare them directly with the load combination that has dead load and live load coming from the moving load analysis. So static analysis enhanced by dynamic factors. Now, this is it for the presentation, and this briefly explains how to run a dynamic analysis for high-speed trains in MIDAS Civil. And now I will go directly into a demo. We will see how to model the geometry, how to set up the eigenvalue analysis, how to apply moving loads, dynamic analysis, and then how to check the results. So for the demo, I have here a model. I simply have materials and some sections. I will use for this, to create my geometry, I will simply use the rail track analysis model wizard. This is used for checking the effects of temperature and train loads, vertical and horizontal loads from high-speed trains when it comes to continuously welded rails. But this time I will just use it to generate my geometry. I will briefly go through it, and in the next webinar my colleague Francesco will explain it more thoroughly. And also in the next MIDAS Civil webinar we will go through the new enhancements brought to the PSC design tool. Now I'll simply load a wizard file, and here I have the material for the deck and the deck arrangement, rail data, section properties, and we can see the placement of the rails and the deck, boundary conditions, so this will create some links between the rails and the deck itself, and also the connection to the substructure. This part will be explained in the next webinar. This is to do with vertical and horizontal loads from trains, but as I said, my colleague will explain it later. And then, very important, just as I mentioned before, in the train load generator, element length is very important when it comes to adding dynamic loads at nodal level. So now I'll simply click OK. and I have my geometry generated. As I said, I have the rails here and the connection between the rails and the deck. Now I will simply modify, just for simplicity, I will consider self-weight and superimposed dead load, so just two static load cases. Now I will change the name of this static load case to self-weight, and I will add another one, let's say superimposed. And now let's add the loads. As I said, static load cases can be converted to masses directly. So I'm adding my self-weight, and also as element loads I'm adding the superimposed dead load. I'll simply select the girder, and let's say we have minus 15 kilonewtons per meter. So now this is all for the geometry. Now to set up the eigenvalue analysis, firstly let's add the masses. So as I said, in structure type we can choose to have the mass added as lump masses or consistent, and we are converting the self-weight, so only the self-weight this time, directly from here. And for the superimposed dead load we will use the function called loads to masses. Here I'm choosing the superimposed load case, scale factor, click add, and now we can see the mass added from this load case. And now we can set up the eigenvalue analysis. So we can go to analysis, eigenvalue. Here we can choose between the different types of analysis and the number of frequencies we're interested in. So let's say 15. And this is all we had to do to set up the eigenvalue analysis. And now to generate, to add the dynamic loads, firstly let's set up the time history load case. So we have the load case here. We can add one, give it a name. Let's say this is speed load model A1. We can choose analysis type. As I said, different types of damping depending on what type of analysis method we are using. I will simply use linear and model, and again, very important, transient time history time. An end time, let's say 15 seconds, an increment, and then for the output, how many increments we want to consider. And then damping, I will simply use the same damping for all vibration modes, so let's say 0.01. And now that we have the time history load case, we can we can generate the train loads. So if we go to tools, data generator, train load data generator, here, as I said, we have different trains available. These are more specifically the KTX in Korea, but we can also define one ourselves. So let's say we have high speed load model A1. Now I will consider a train velocity of 320 kilometers per hour, and as I've mentioned before, my element size is 1 meter. And here we can simply define, as I said, the length and the force, but I will simply import a file. So here I have simply my axle number, distance to the next axle, and the loading, and I will simply import this. So if we go to here, load generator, data, now we have all the information for the train in. Simply click OK, and this is the load generated directly. We can save this, so let's say high speed load model A1 320 kilometers per hour. And now we can close this, we don't need it anymore. And now that we have the load generated, we need to import it as a function. As I said, we will apply the load simply at node level, and then the function will come with the loading on each node. Now we go to loads, dynamic loads, and define the function itself. So time history load function. We can, as I said, there are different types of applying dynamic loads, and we can even convert from any static load case. We can convert them to dynamic loads directly, but I will just add a function now. Here we have, if we're analyzing earthquakes, we have different accelerogram that we can use, but now I'll simply import the function for the train load that I've just created. So train load generator, and now I have my load, and we can see the values over time. I have a name for it, close. And now, as I said, it is basically up to us where we want to apply the dynamic loads, but now that I have the rail, I can apply it directly to the rail. But in order to make it easier for us when we are going to use the MCT command shell, I will simply renumber all the nodes. So now if I isolate the track and display the node numbers, we can see that we go from 2, and the order is not, so they're not ordered one after the other. So what I will do is simply renumber them. So from node element, we go to renumbering, only the selected ones, and we start from 1 on this side. I will consider that I have 2 trains running on the bridge, but in opposite directions. So I will have this going from along x positive from 1 to the end. So now I have 1 to the end, which is 121, and this time, and from this end I will need to go the other way around, and I will go from 122, but this time along x minus. So now we have 122 up to 242. Now that we have the renumbering, we can directly apply the train load to one node. So from load, dynamic node loads, here I have the time history load case that I've mentioned, so this. And here we have the function name, so this one. So this one. So we simply select the load, select the direction. Scale factor will be -1 as it acts in the negative direction of z. And this is the first node that gets loaded, so arrival time is 0. We select node 1, so we see here node 1, and apply it. Now, as I said, we can apply it manually to all the loads, but it's much easier to use the MCT command shell. So if we go to Tools, MCT command shell, and here type in asterisk, then node load, and insert data. So this is how this load looks in code based. So now if we take this and copy it into an Excel, we can create a spreadsheet that can easily generate the load. Very important it is to copy this, but then delete it from the spreadsheet so we don't apply it twice. So I'll simply cut it from here. And now I have this spreadsheet here. I have the velocity of my train and in kilometers per hour, and then converted into meters per second, and the spacing between two nodes, 1 meter, and then these are the arrival times for the new nodes, so where we will apply the new load. Now we paste this here. This is the node number, so we can cut all of this here, and now we have the direction and arrival time. Direction, arrival time, and for the new node we paste this here as values, and that now we're starting from node 2. And the same thing can be used for this time node 122. We start from 0 and then arrival time, paste the values. Now this will be 3, 4, copy it here, 5, and then this one simply copy the same, and this direction -1, and we can do the same for the other tracks, so 123, 124, copy the same, this doesn't change, and copy this here. And now we can generate, so we had, as I've mentioned before, nodes 1 to 121 here, and node 122 to 242. So now if we go back, we can generate to 121. So we have 121 and 242 should be here. So 242. And now we can simply copy these into the MCT command shell. So as I said before, we're not copying node 1 again because this load is already applied, so it is already here. We simply paste this and then add the other direction, the other track, copy and paste, and now we have one load here, run, and now we have 242 nodes, know the loads, can display them, and we can see all the loads along the bridge. And this is all we've had to do to set up a one-time history load case. And as I said, we also need to compare these results to moving loads. So I will briefly show how to apply moving loads as well. So for moving loads, we can choose a code, define some tracks. So let's say track 1, centricity 0, spacing 1.435, going from this node, and click apply, and track 2, this time going from this node to this node. We can also add vehicles. For simplicity, I will just consider one load case. So let's say we have high-speed load models. We can apply here the dynamic factors. We calculate them and add them directly here. We can also consider the distribution of the loads, and also if we have eccentricity, lateral displacement of vertical loads, so the eccentricity coming from this. And to create the load cases, the moving load case, we can simply add one, choose bridge type. Here we have the psi factors, we can consider them or ignore them, and we can choose a vehicle, which of how many minimum number of loaded lanes and maximum number, and the scale factor if we want to consider, and the two tracks. And let's give it a name, high-speed load model A1. Okay, and once we've done all of these, another important thing to consider is the setup for the moving load. As you know, for highway bridges, loads such as load model 1 can be separated, and the loaded length can be changed along the bridge. But for trains, this is not possible. The train is just a continuous train, so we need to choose all points in order to make sure that the train will not be split when the load is applied to the bridge, and simply press OK, and then we can run this model. to save time, I have a model that I've already analyzed. So I have it right here, just the same structure, same load, but analyzed. I forgot to mention, so for the analysis, for the moving load analysis, we can consider dynamic factors for railways directly here, for load model 71, SW0 and SW2. Now once I've analyzed the structure, we can firstly check vibration modes. So mode shapes, we can show the legend and check the vibration modes. So we have mode 1. We can check the shape and period of vibration, the natural period, and we can do this for all modes. Or an easier way of doing this is by checking actually table results. So if you go to results tables, vibration modes, and here we can check the periods and frequencies for all modes, and then modal participation factors. We can see along each direction, and we can see how much mass is excited in the structure, and then a modal participation factor, just the printout, and we can also check vibration modes from here. And once we've checked these, we can continue with checking accelerations. So checking time history load cases, we can check displacements and accelerations, and we can choose any time step for the time history load case. We can check the shape and even plot the legend. But maybe for this type of check, the easiest way is to actually do it in a graph. So we can set up graphs for every node along the bridge. So now, for example, I can define one, add a new function, give it a name, choose a node number, let's say node 283, sorry, 283. Acceleration, we can choose to consider it as a reference to the ground, or add the ground motion to it and choose a direction for it. Click OK, and then we can go back. So we can go to the graph directly and choose which of this we want to check. So let's say we want to check two nodes at the same time. We can give it a name. Sure. How many decimals we want to consider for each result. We can directly see a graph. So we can check for more than one node at a time. We can zoom in, zoom out. We can check it just for one if we want. So let's say we're interested in this one. And when we do these checks, we need to make sure that we have enough, that we've set up enough time for the time history load case so that the accelerations reach zero level. And once we have the histogram, we can, as I said, apply a fast Fourier transformation and see in what where most energy goes, in what frequencies from the excitation coming from the train load, in which frequencies it mostly goes. So we can see a peak here, and then some small ones here. We can zoom in here and check the actual frequency in hertz, and we can compare this directly to the periods, the frequencies, natural frequencies of the structure. Now once we've checked this, we need to also check the results of the static loads enhanced by dynamic loads, by dynamic factors against dynamic analysis. Now for this, we can create load combinations, as I said. So from results, we can create load combinations. So let's say I have one with the results coming from the moving load analysis. have the self-weight. I've just considered a factor of 1 for this example, and choose the moving load case, so MV. And then time history, I have the same load, but then I'm using TH load case, so time history load case. And then we can simply go and check the results. So let's say we're interested in diagrams. We can check the results for any static load case directly. Or we can go and check, just as I said, envelope results, max, min, or all. So this is the load combination for the moving loads. So envelope results for the moving loads plus dead load, and then time history load case plus dead loads, and we can compare the results. If we can do it visually, we can do it in results tables just as we would do for any other load. Now this is it for the session.